Okay, so we're going to start with the projectile motion equation from the 2015 administration of the AP exam. This one deals with projectile motion, conservation of momentum, conservation of energy, and so it's a generally robust problem for some simple ideas. So we're going to start out and we're going to consider the fact that we start out with some initial mass for a dart that's launched at a certain angle with an initial speed v0 of 10. It sticks to a mass of 0.10. The string is 1.2 meters long, presumably, although they say the center of mass, so that's a better description. And it rises through angle theta at the top. And air resistance is negligible. So starting out, we'll consider that this velocity actually has a component upward and a component sideways. That sideways component of the velocity is whatever that initial velocity is times cosine of 30, and the horizontal and the vertical component is v0 sine 30. And going through this, you'd say, okay, well, why does that help me? Well, it turns out that the collision happens at the apex, and at the apex we know that Vy has to equal 0. We're just moving horizontally with Vx. Now Vx is the only speed that this block will have. The Vx hasn't been affected by any force, so it hasn't changed based on Newton's first law. So here, the Vx is my V0, which is 10, times the cosine, the horizontal component, or of the launch angle. And so if we look at this, what we get if we put this into a calculator is that Vx equals 8.7 meters per second. This is a 1-point answer, and it's just determining the vertical velocity or the horizontal velocity. Now we want to know the horizontal distance d until it impacts, which means we want to know how long till we reach Vy equals 0, until we reach that apex. And when we find that time, we can find the distance traveled with the horizontal speed. So the way we'll find this, how long do we reach till we reach Vy equals 0? Well, we know the final speed in Vy final is equal to the Vy initial plus a t, where a is a negative value, negative 9.81 or negative 10 meters per second squared. And if I use 9.81, negative 9.81, I'll find that I have Vy final, which is what? What is this value? This is actually a 0. So 0 equals Vy initial, 10 sine 30, which is just, sine 30 is 0.5, so this is just 5, plus negative 10 t, or negative 9.81 t. If we solve this out algebraically, we get negative 5 over negative 10 equals t, which equals 0.5 seconds, which is an answer that we are permitted to use. If we use 9.81, we get t equals 0.51 seconds. We decelerate a little slower. It takes us a little longer to reach the apex. So this tells us, given that we know our speed to be final speed to be 0 at this point, we plug in our initial values and the strength of gravity, the acceleration due to gravity, and we find the time that it takes to reach the apex. Once we have the time, we can say that the distance d is equal to the Vx times that time. So we have both of these values, so the Vx value is 8.7 meters per second, and the time value is 0.5 seconds. So we get a distance of 4.35 meters, if I did my math correctly. Or, if we want to round to two significant digits, it would be 4.4 meters. So this part would be this part here, B, is 2 points, and that is this value here. So I'm going to move this down so that we have a little more space to work. And so that is this part. So let's look at the speed of the block after the dart strikes, just after the dart strikes. So the speed of the block. Well, we know that the block has a mass of 0.1. The mass of the dart is 0.020 kilograms. The speed of the dart when it hits is 8.7 meters per second, and we know that the speed of the block is 0 at the start. So this is able to give me my momentum to begin. And that's got to equal my P after, which has to equal, well, the dart has stuck into the block, so the masses are combined. Times the VF, the final velocity, which they share because one has stuck into the other. So if I calculate the momentum before, well, I'd see that it's equal to just the mass of the block, or mass of the dart, 0.20 times 8.7 meters per second. And that's going to equal 1.12 kilograms times VF. I divide each side by 0.12 kilograms. And I get something equivalent to about, when I divide each side by 0.12, I will get that VF is approximately equal to 1.4 meters per second. So that's the speed of the combined objects when they stick together. So now we have to worry about the angle through which the dart and the block on the string will rise before momentarily coming to rest. So how would we go about doing this? Well, the easiest way to deal with this, the easiest way, is to consider energy. If I scroll back up here, you'll notice that I start out with some energy here relative to where the block stands. I could say that my PE relative to that position is equal to 0. I could say that my KE is equal to 1/2 of the combined masses squared times the velocity squared. that VF that we just found, that 1.4 meters per second, and that at this point, at the very apex, my KE has got to be equal to 0, and that my PE is going to be equal to that value. And once I have that, I know how much I rose in height, this value. I know how long, therefore, this section is, because it's just 1.2 minus how much I rose. And then I know the angle because I know that this section is 1.2 meters. 1.2 meters for this side. 1.2 minus how much I rose based on my potential energy for this side. And then from that I can calculate an angle. So let's scroll down and figure that out. So the energy to start is the start versus end have to be equal. I have 0 for the potential energy plus 1/2 m1, which is 0.020 plus 1 or 0.1 times 1.4 squared, and that's equal to the mgh, which is 0.020 plus 0.1 times g times h. Well, the nice thing is that this part and this part will cancel out, and so I'm left with 1.4 squared over 2 equals GH. So divide by G. I'm left with that height from here to here, if this is the block, the height from here to here, h, that I rose, is equal to 1.4 squared over 2g. And the actual value of that is going to be something equivalent to well, we'll calculate that in a moment. It's important also, though, to consider that this height really is equal to the length minus the length minus how much we have here is equal to the height, and that height, that length there is, if we project this string down, we'll find that that's the length times the cosine of the angle theta. So if we plug in here, we see that the height is 1.4 squared over 2g equals L minus L cosine theta. And from there we can calculate we can do some rearrangement and find the actual value of the angle. And to find the value of the angle, we'll find that it's about, if you go through the algebra here, 24 degrees. And so we have 24 degrees here, where if you plug in the values for this length as 1.2, we'll find that we have 24 degrees for theta. And so when we know so we know this value is sort of important for the next part, or for part F of this problem. The block then continues to swing as a simple pendulum. Calculate the time when the dart collides with the block and when the block returns to the original position, which means find the period. And we know that the period equation for a simple pendulum, given that we're within certain bounds, the period equation equals 2 pi root L over G. Well, we have all those values. It's only dependent on the length of the block, and so, or the length of the string on the block. And if I plug in those values, I get about 2.2 seconds for the period. But the thing is, this isn't asking for the full period. What this is asking for is, from the time I hit, how long does it take to go out and back to the original point? Not how long does it take to repeat that on the other side. And so really, we have to divide this by 2, and we get 1.1 seconds equals the time. So, finally, we have to consider some conceptual questions. In a second experiment, a dart with more mass is launched at the same speed and angle. Dart collides with and sticks to the same wooden block. Would the angle increase, decrease, or stay the same? Well, we have more mass, and so therefore we can transfer more momentum, and therefore we have more velocity at the end. And so the angle would have to increase, greater speed, is a greater height, which yields a greater angle. Likewise, we want to consider the period of oscillation. Would it increase, decrease, or stay the same? Well, this is a sort of a tricky question. And the reason is because we have this idea of, okay, well, we have this simplified version of a period equation. Where we would say that, well, period does not depend on mass. Based on the equation that we know, so we'd say stay the same. However, the problem is that technically we have an issue with this, because the full equation here is much extended. We've simplified this equation based on something called the small angle approximation. And the idea is that when we have some pendulum that goes really high past a certain point, well, the problem is that we have gravity, a component of gravity affecting it in a slightly different way. We lose some tension in the string, and we are actually sort of in free fall at some point. So that section ends up going faster than it would in a normal pendulum. To some ideas about torque. And let's just clean this up a little bit. Okay, so let's switch gears and talk about rotational values, understanding that theta is equivalent to x or s over r. Omega is equivalent to v over r, and alpha is equivalent to a over r. These will be useful conversions later on in the problem we're about to hit. Additionally, it's important to understand that torque is equivalent to r cross f, and that or rf sine theta, and additionally, it's important to understand that torque is we have this sort of rotational analog of the second law of Newton, that this is the rotational inertia times alpha, the angular acceleration. So that will tell us how much torque is necessary to accelerate an object of a certain rotational inertia value. And we're given in this problem a rotational inertia value. So here we're trying to figure out a few different things. This is a problem where we have a pulley, which has mass, okay? So this pulley has some mass. It's a massive pulley, and a massive pulley is sort of this interesting thing because, well, now we can't discount it in a problem. If we have a massless pulley, it doesn't take away from, it doesn't add any rotational energy to the system when it rotates, because its mass is zero. So for our purposes, we're going to consider a situation like this differently to some extent than what we'd consider a situation with a massless pulley. So a pulley of radius r1 and rotational inertia I1 is mounted on an axle with negligible friction. A light cord passing over the pulley. Light cord indicates we're not considering the mass. The mass is about 0. And it has two blocks of mass on either side, mass m. Assume the cord does not slip. Determine the answers in terms of m, r1, I1, and fundamental constants like gravity. So what is the tension in the cord? Well, the tension in the cord, well, the only way to figure that out is to say, okay, well, given this is hanging, given this is just sort of hanging, that there is an acceleration of 0, that the sum of the forces is equal to ma, then what we can see is that, well, we have on the left side, we have 2 ma. If we draw a sort of free body diagram here, we have this block where we have 2ma, or 2m, with tension pulling up and Fg pulling down. Well, we can see that if the acceleration is 0, then the tension minus the force of gravity this should be G. The tension minus the force of gravity is equal to ma, which 2ma, which equals 0. Now, therefore, the tension minus, well, what's the force of gravity? It's just 2mg. That equals 0. So the tension has to equal 2mg, given that we're not accelerating. Why are we not accelerating? Well, you can tell we're not accelerating because this and this are equivalent. So there's no force on one side that's unbalanced compared to another. So in this case, the tension of the cord is 2 mg. And this would work on either side. Should probably draw a free body diagram. It's a pretty useful tool. So let's move down, and let's say one block is now removed from the right and hung on the left. When the system is released from rest, the 3 blocks on the left accelerate downward with acceleration g over 3. Determine the following: the tension in the cord supporting the 3 blocks on the left, the tension in the section of the cord supporting the single block on the right, and the rotational inertia of the pulley. So take a minute and try it out yourself. And hopefully the first thing that you did was draw a free body diagram. Well, we know for sure that we have this area of 3m with some force of gravity and some tension. That's T3. And we know that it's accelerating downward with A equals g over 3. This Fg value is 3 mg. And so we have to set up a similar equation to last time, where the sum of the forces is 3m times A. But we know the A value here. So the sum of the forces, tension 3, which is sort of holding against gravity, going the opposite direction of gravity, and we have a 3 mg here. 3 mg, the force downward, the greater force, subtracting the smaller force T3, equals 3 m times g over 3. Well, when we look at this, we'll see that we have 3 mg over 3 is just mg. And if we subtract that from both sides, we get 2 mg minus T3 equals 0, and we get 2 mg equals T3. Well, that's convenient. It's the same tension. Now, what is the tension in the cord supporting the single block at the right? The tension in that cord up here, now that we have taken one of these away, now that we've taken one of these away, and moved it to the other side, well, we just have 1 mg there, and that is accelerating upward. So while solving this, we're going to assume that we have an A. Let's do another free body diagram there. We have a mass m. We have a tension T1. We have a force of gravity equal to mg. And we have an acceleration upward of A equals g over 3. And so if we were to set this into an equation, we see that the sum of the forces is equal to ma, and the sum of the forces this time is T1 minus mg. Because the force is going upward, the magnitude total is going to be the tension force, the bigger force, minus the smaller force, mg. That's going to be equal to m times g over 3. If we add mg to both sides, we find that T1 is equal to 4/3 mg. So we have a lighter tension in that right-hand cord, in order to instill an acceleration of A over 3, or of g over 3. finally, to find the rotational inertia of the pulley, there are a few things that we have to do. We know that torque is equal to the rotational inertia I1 times alpha, and at that point we can say, okay, well, I know for sure that this alpha value is based on my initial equations up top, A over R, and I know A, so this is pretty convenient. And I know my R value. The R value is R1. So if I wanted to rewrite this, I could say that A over R1 is equal to alpha, and likewise, that is also equal to G over 3 R1. That's a useful value to have. Okay, so that's what the alpha value is. And in general, we also know that torque is equal to the tangential force times the radius that that force is applied at, or R cross F. And if we take this this force, well, what is that force? That force is actually going to be, I have this force downward, this tension downward on that side. I also have a tension downward on that side. This one is 4/3 mg. This one is 2 mg. And so we see that we have a net counterclockwise torque, a net positive torque of 2 mg minus 4/3 mg. And that could be the value here. This is my tension 3 minus my tension 1 times the R1 value. And that's a torque value. And if I were to look at this, I'd say, oh, well, that's equal to 2/3 mg times R1. And so that has to be equal to the torque that I get by considering I1 alpha. I1 times alpha, but alpha is G over 3 times R1. If I multiply both sides by R1, by 3R1, I get 2 mg R1 squared equals I1g. Divide each side by g. I get I1 equals 2m times R1 squared, which is convenient because I know that the value for I, the unit, should be kilogram meters squared. Well, I have here my kilogram in mass, and here in R1 I might have my meters, and that value is squared, and they're multiplied together, so the unit is correct. So I know that the answer is reasonable here, and I haven't screwed up my multiplication or division. So this value is the rotational inertia of the pulley. So let's move on to the next part. So the blocks are now removed, and the cord is tied into a loop, which is passed around the original pulley and a second pulley that's way bigger. Rotational inertia that's 16 times as big as I1, which we have just calculated. And the radius is 2R1. The axis of the original pulley is attached to a motor. There's a motor right there. that rotates it at an angular speed of 1, which in turn causes the larger pulley to rotate. The loop does not slip on the pulleys. Determine the following in terms of I1, R1, and angular speed L. This is an L. And L. So the angular speed of the larger pulley. Well, the angular speed is an interesting thing, because if this were continuing that way at some speed, some velocity, and this rope, this cord is not this cord is not like being stretched or shrunk or anything like that, then the velocity of the cord has to be the velocity of the cord. So whatever the speed of the cord is has to be the same either way. So if the speed of the cord is the same either way, then what we're going to have to say is that, well, if the V of the cord in one area is equal to the V of the cord in the other area, let's say right here, and the tangential speed right there, those V values, if I consider those to be, say, a V1 and a V2, those should be the same, just because of the nature of the cord. The cord is moving at some speed. It can't change the speed at which it's moving, otherwise it'd either sort of compress up at different points or it'd rip apart at different points. Like if it were moving faster here than here, it would be stretching out. If it were moving faster here than here, it would be compressing up. So this cord has to be moving at the same speed either way. Now, we do know a conversion there, that the V value is equal to, if we see that omega equals V over R, then V equals omega R. Well, let's just do that. We know the omega here, omega 1 times R1 has to equal omega 2, which we don't know. This is angular speed omega 2 of the larger pulley. Omega 2 times R2. Well, but how big is R2? So this we would say omega 1 R1 is equal to omega 2. Well, based on this, R2 is just 2R1. So I divide both sides by 2R1 to find omega 2, and I find that omega 1 over 2, because these cancel, is equal to omega 2. So this is moving with an angular speed half the angular speed of this. That's an interesting idea. This is related to gears and things like that. Now we want to know the angular momentum of the larger pulley. Well, the angular momentum can easily be seen to be, we could calculate this a couple different ways, but in general, the way that we're looking at here with the information we have is I omega. We know the I value, and we can calculate the, and we know the omega value, and we're allowed to use a few different pieces of information here. We also have, we can also use omega 1 here, because that's given. So what we're going to say is that, well, we know the rotational inertia here. We know the angular momentum, or the angular speed, rather. And if we plug these in, we just get L equals 8I1 times omega 1. This half in this 16 turned into an 8. And that is sufficient. So this is the angular momentum of the larger pulley. And what is the total kinetic energy of the system? Well, this would be the speed, the kinetic energy of the first pulley plus the kinetic energy of the second pulley. Well, kinetic energy of the first pulley is 1/2 I omega squared, where the I1 omega 1 squared, plus the rotational energy of the second pulley, 1/2 times 16 I1 times omega 1 over 2 squared, the omega 2 value. And so if we plug these in and we multiply them out, what we get here is a omega 1 squared, so this is 1/2 times omega 1 squared over 4, so 4I1 omega 1 squared, and this would be plus 1/2 I1 omega 1 squared, and that would mean 2 here, plus 1/2 is 5/2 I1 omega 1 squared equals KE total. So some simple algebra based on the ideas given in this problem. And that is it for this problem. I encourage you to run through and try this out on your own, of course, before I do it. You'll get more out of it that way. But if we look at these two problems, a bunch of different ideas, but they combine, typically rotation problems will combine a lot about the rotational kinematics, or the or linking torques and forces, linking tensions and torques, and so you have to keep in mind all of these equations. But needless to say, we have an idea in general of Newton's 3 laws, Newton's third law, equal and opposite, which defines interactions, defines a force as an interaction. And 2, which defines the size of that interaction. As a vector equation. And then N1, which is just a special case of N2, when A equals 0, F equals 0, sum of the forces equals 0, or, and A is not equal 0, implies that the sum of the forces is not equal to 0. So these are some important ideas that can really apply to either of the problems that we dealt with earlier. With projectile motion, the idea that the Vx is not changing comes from the fact that we have no forces, therefore no horizontal acceleration. However, the Vy value does change because in projectile motion problems, the sum of the forces is equal to the mass times the gravity. Therefore, the acceleration is gravity, which is pointing downward, which decreases my vertical velocity, which then allows me to find all sorts of things about the problem. Okay, so likewise with the torques, equal and opposite interactions, this will often let you find all sorts of minor problems out and set up your free body diagrams correctly. Some of the forces to determine accelerations, or when you know accelerations, you know you have certain forces. When you don't have accelerations, you know you don't. Okay, I think I'm going to leave this problem here, or this video here. Good luck on your tests. Send me emails if you have questions.